Hello and welcome to the lecture on Lighthouse Project at Chennai. My name is Shailesh Agrawal, Executive Director of Building Materials and Technology Promotion Council, and I'm going to educate you all through this presentation about the field level implementation of innovative construction system being used in this Lighthouse project, including design basis, materials, manufacturing, structural drawings, detailing, and actual site photographs explaining the different construction stages. The outline of my lecture is as follows, starting from Global Housing Technology Challenge India and Lighthouse projects, the technology in terms of structural elements, namely foundation, structural system, floor slabs, and wall panels will be discussed, followed by construction activities at site. Ministry of Housing and Urban Affairs organized Global Housing Technology Challenge India in 2019, and Construction Technology India Exposition come exhibition was organized during Global Housing Technology Challenge, which was inaugurated by Honorable Prime Minister of India. The objective of Global Housing Technology India was to identify and shortlist a basket of construction systems which can help build maximum number of houses in minimum time and at minimum cost. Through this challenge, we could create a basket of 54 new innovative construction technologies, which are broadly classified or categorized into these six broad categories, which are written here. There are two categories of precast concrete construction system, which is 3D volumetric, and another one is 2D planar. And in addition to these two categories, there are four other categories, namely steel structural system and cold form steel structural system, prefabricated sandwich panel system, and engineered formwork system, as well as stay in place formwork system. Today, I am going to discuss with you precast concrete construction system in detail. Let me tell you about the six lighthouse projects which are right now being implemented in different states of India. This table shows the city where these projects are being undertaken at present. And as you can see, at all the six places, more than 1,000 houses are being constructed with those six broad categories, and with six distinct technologies under each broad category is being used in these projects. So today I'm covering the project, Lighthouse Project at Chennai, where we are using precast concrete construction technology. Let me very briefly give you the project brief. The project comprises of 12 blocks, and each block is of 6 story. These are the blocks 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And in addition to the housing, we are also providing physical infrastructure as well as social infrastructure. If you look at the typical floor plan, at each floor, there are 16 dwelling units. Let's have a look on the dwelling unit, individual dwelling unit plan. And as you can see, each dwelling unit comprises of one hall, one bedroom, a kitchen, bath, and WC with separate access to bath and WC from both the rooms. Also, one thing which is noteworthy here is that all these dwelling unit plans conform to the space norms given in National Building Code 2016. National Building Code 2016 specifies minimum room sizes along with width of a staircase, height of kitchen, and other space parameters for EWS housing. So all these dwelling unit plans comply with those National Building Code norms. In addition to National Building Code conformance, we are also incorporating other special features such as green rating as per GRIHA. Also, renewable resources are being encouraged in terms of rainwater harvesting and solar lighting, solid waste management, and sewage treatment plant with recycling of wastewater is also included in the project. Firefighting services as per NBC norms are also included. Let me now give you the brief about the technology. First, I will tell you in general the technology being used, and then we will get down to the specific. Dear Technoguys, we all know the way construction takes place world over. So on the left-hand side, if you see these two pictures, which shows the prevalent construction practices. And what are those prevalent construction practices? One is load-bearing structure, where walls are constructed brick by brick by laying bricks and creating a wall, and over those walls are cast in situ RCC slab or sloping roofs are laid. So that is one prevalent construction system. And other one is RCC framed structure, where cast in situ beam columns are cast, and then slab is laid, and then walls are filled as infill walls. So these are two typical construction systems, and all of you know that these systems over the years have become unsustainable, because there is wastage of material. They make use of material which are based on finite natural resources. They also, most of these projects are caught in time overrun and cost overrun. I mean to say, by time overrun and cost overrun, when you start a project and by the end, by the time project is completed, there is a the time overrun and cost overrun. Suppose the project was started with a X amount. The moment by the time you finish the project, the cost escalates many times, and it happens because these construction practices are primarily slow in nature. Also, it has been found that there is noise pollution, there is air pollution, a lot of dust is being created when we use these construction systems. So friends, we need to replace these construction practices in vogue by innovative construction systems which are speedier, sustainable, and amenable to our environment. And one such category is precast concrete construction. As you can see, what about, replacing this cast in situ, this is a beam and this is a column, by factory made beam and columns. So this on right hand side, what you see is schematic diagram. Here in Chennai, what we are doing is we are using, this is a column and this is a beam. These are RCC hollow columns and precast RCC beams, which are cast either in the factory or in a casting yard near to the site under controlled conditions. And then they are transported to the site, assembled in such a fashion, and over which again partially precast slab is laid. Similarly, other structural elements such as precast staircase is again cast in the factory and then assembled at the site, and all these things are then bed jointed. You can have this infill. Here in this project, we are using AAC block. Otherwise, you can also replace this AAC walls or masonry wall by drywall, which can be manufactured in the factory or in the casting yard, or by a concrete wall as well. The foundation here is conventional because depending upon the soil condition, soil strata, water table, foundation is kept conventional. So we are trying to replace our construction systems which exist by precast concrete components, structural components, which are made in the factory under controlled conditions. Now, let me explain you briefly the various structural elements. This typical slide, which I also showed you in the previous, just to explain you what is building. Building comprises of a substructure and a superstructure. Substructure is nothing but a foundation and a column or a pedestal up to plinth, and over plinth, these vertical elements which are called columns, and then these horizontal elements which are called beams are laid, over which a floor or slab is laid. So this Beam column system is called structural system. This is called floor and slab, and this is called walling system. So I will explain you all these systems one by one. I just wanted to explain you that this structural system is nothing but the skeleton of your building. So this framing, beam column framing is nothing but a structural system. So foundation, as I told you earlier, that foundation we are using conventional here, and again based on the geotechnical investigation, bearing capacity of the soil, the soil strata, subsurface soil strata, the depth of water table, the foundation is decided. It is then designed. The depth of foundation is also decided, and then these foundations are laid. Here we are using isolated and combined footing, which is a conventional RCC footing. And once the foundation is laid, over that you can lay the plinth, pedestal, RCC columns. They are also known as stem columns. Then once as you can see in this slide, this is your foundation, and over the foundation a pedestal, which is also known as stem column, that is raised up to plinth level, and plinth level is the level which is your natural or finished ground level. And over that plinth level, you connect all the columns by plinth beams. Okay, so foundation is connected to the plinth through these stem columns, and in this project these stem columns are also cast in the casting yard. So under controlled condition, these kind of stem columns are cast. Similarly, these beams are also cast in the casting yard, and both of these columns and plinth beam are then aligned, erected, and they are wet jointed. I also want to stress here that in order to have better seismic resistance, it is always advisable to connect all the footings, if they are scattered footings, at the plinth level by plinth beam. This will ensure integral box-like action and will help in improving the seismic resistance of a building greatly. Now, as I was explaining you, these beam column or skeleton or frame is called structural system. Structural system is the skeleton of a building, and this is primarily responsible for transferring the load of the building to the foundation safely. So if our structural system is not robust, the building is bound to have failures, or will not serve the purpose for which it is intended to. So here, the system being used, because it's a patented technology, the system which is being used is industrialized 3S prefab system. Prefab means prefabricated system, where all these structural components which I just explained you, columns are vertical members, beam are horizontal members, and shear walls, facades, slabs, and staircase, all of them are cast in the factory, then transported to the site, aligned, erected, and then joined together to construct the building. Okay, and in this project we are using this filler. As you can see here, this is AAC block filler walls. The variation could be, instead of these AAC blocks, you can use the ready-made wall, a concrete wall, which can be cast in the casting yard, or else you can use a dry walling system comprising of sandwich panel systems. Okay, but in this project, we are using precast RCC column, beam, partially precast slabs, and then once the skeleton is erected, then the walls are of AAC blocks, which I will also explain later. Let's move to the another structural element which is very important, and that is slab. Normally the slab is cast in situ in conventional system, where first formwork, first shuttering is done, then formwork is laid, over which reinforcement is laid, and then cast in situ concreting is being done. What about changing that cast in situ process by bringing factory-made slabs and just putting them over the beam column frame, and then doing the screen? So That is what is being done here. What you see here, this is the slab, which is the entire slab, depending upon the size of your room or your size of your project. These slabs are cast in the factory, and then they are hoisted at the site, then aligned, and then in order to have monolithic connections, the screed. Screed is something which is small, a thin concrete layer with reinforcement, and the thickness is around 75 to 100 to create a monolithic connection. What happens? This is a beam, and there is a column, and when the slab is laid, you need to connect this slab with this beam and column, and therefore what you do is you put a concrete layer with reinforcement and fill these joints in situ. That will ensure integral monolithic action. Monolithicity means here that, or in case of earthquake, or in case of any other load, the building will act together in a box like fashion. Let's move to the next structural element, which is wall. And here the walls are made of autoclaved aerated concrete blocks, which I will also explain when I will show you the site photographs. These AAC blocks are replacement to the burnt clay brick. They are lightweight. And why they are lightweight? Because here you don't use aggregates, but that aggregate is replaced by foam. And being light in weight, they offer a lot of advantages. The dead load of building is considerably reduced, and their size is also larger than your brick size, so you can quickly lay the infill walls. But one thing to remember here is that these AC blocks can only be used as non-load bearing infill walls. Before I get into the construction sequence, the advantages of these factory-made building components are written here, and the advantages are so many. Some of them are written. I will try to explain you them one by one. First of all, if you compare the cast in situ construction with the factory-made construction, you will realize that quality control and is better when you do something in the factory, because there you are doing under controlled condition. In the factory, if you manufacture something, you do it under controlled conditions. So building components are made in the factory in a similar fashion as you do in an automobile industry. So each building component is, as far as dimensional accuracy is concerned, as far as material consumption is concerned, as far as the reinforcement, other structural details are concerned, all of them are maintained at a higher standards. And once you maintain the quality at higher standards, what happens? Once the building is put to use, or those construction elements, structural elements are put to use, they will not require any maintenance, or they will require less maintenance. And less maintenance means the life cycle cost of the building will get reduced. There will not be leakages, and the building will behave better in case of any external in case of disaster. Secondly, when you do everything in the factory, naturally there is considerable reduction in pollution, whether it is dust, whether it is air, whether it is noise. Also, because you are using cement concrete, and cement is based on a natural resource, there is significant reduction in wastage of these precious resources, because you are optimizing use of the material. Also, when we use concrete, water is significantly used for curing of component here. In these systems, there is significant reduction in use of water. Friends, also, it has been found during COVID time that safety of workforce is sometimes compromised at site. So once you take the entire construction activities in the factory, you ensure safety and well-being of the workforce which is being put for the project. Also, the speed is also one of the most important parameter, which is which can be achieved by employing these kind of construction practices. Because beforehand you decide everything. So that is why these are called pre-engineered buildings as well. So you procure all the elements, all the materials, you pre-plan everything, and once everything is planned, then you can start manufacturing those components, and the entire process can be industrialized, automated, so that speed is achieved. And once you finish the project well within the time, you save on cost as well. Also, there is the clauses like cost escalations can be avoided. Limitations, there are a lot of questions being asked that these technologies are expensive, but let me tell you here that they are capital intensive to start with. But once you have sufficient number of houses, of sufficient number of construction activities using that technology, the rate goes down. So if you give a minimum number of houses, or a minimum, a critical mass, the technologies, this system becomes comparable with conventional cost of construction. Another limitation, if we need to say, is use of skilled manpower. So because all these components are done in the factory and under highly controlled conditions using sophisticated equipments and sophisticated processes, therefore you require skilled manpower. Now, most of these projects, because they are using new technologies and this kind of mass scale field implementation of these new technologies taking place for the first time. So all these lighthouse projects are awarded on design and build basis. And design and build basis means that we provide the plot with specifications and list of international national standard, and then ask the agency to design as per these specifications and national and international standards, and then build the structure. So that is why it is called design and build basis, which is very popular in case of highways, and now the same is being promoted and being advocated in housing construction as well. So here, this project is being done by BG Shirke Construction Technology Private Limited, which is one of the leading agency in India as far as precast concrete construction is concerned. So the design philosophy is very important whenever a project is undertaken. You need to first spell out what is your design philosophy. So in case of a building, what comes to mind is that the building should be able to serve the purpose for which it is intended to build during its service life. So there are criteria like limit state of serviceability, limit state of collapse, so that that kind of limit states need to be incorporated in design philosophy. So also the structure which is being designed should perform satisfactorily during its intended life as per the guidelines which are laid down in the relevant Indian standard. So here primarily it is a concrete structure. So there is a Indian standard IS 456. So the design philosophy is based on Indian standard 456. Then there is a limit state method which is adopted, and that limit state method ensures the intended durability and serviceability requirements. Also, there are other standards such as 13920, which is a ductility code to ensure ductile behavior of a building during earthquake. And that code is also very important because that makes your building ductile, and that will ensure that there is no loss of life in the event of an earthquake. Limit state, when we are using limit state, there are several provisions that what should be the water cement ratio, what should be the minimum cement content, what should be the minimum percentage of steel, how to detail the reinforcement, how reinforcement is curtailed, and how the reinforcement which is how the reinforcements are being connected. So all these things need to be incorporated. Let me briefly tell you about the water cement ratio and minimum cement content, because whenever you are doing a concrete structure, you need to have a mixed design, and in mixed design, whenever you do a mixed design, minimum cement content is laid down by Indian standards, so that need to be kept. So that minimum cement content for, suppose you're doing M20 concrete, so suppose it is 300 kg per meter cube, so that need to be maintained. Another thing is water cement ratio. What happens when you do a construction at site? It is found that in order to make concrete workable, we keep on adding water, but adding that water makes your concrete very, so maximum water cement ratio need to be ensured. Also, to avoid bad design, to avoid bad detailing, minimum percentages of steel, that is a bare minimum, whether it is required or not, but that minimum percentage of steel is to be given to ensure durability and serviceability. So based on this, the design basis, let me just briefly tell you, first of all, soil investigation is done, and based on soil investigation, bearing capacity of that area is found, and that based on that bearing capacity, normally foundation is designed, and also the depth of foundation is decided. So in case of Chennai, the safe bearing capacity is 25 ton per meter square, and depth of foundation varies from 2.5 to 3.5 meter. Then based on this safe bearing capacity, there are Indian standards available for different kinds of footings. Here we are using shallow foundation, which means isolated and combined footing. So there is Indian standard 1080 and 1904, with which the foundations based on this safe bearing capacity and depth of foundation are designed. Also, another design parameter is the grade of concrete, because here we are using precast concrete. So normally for precast concrete, because elements are thinner, so higher grade of concrete is required. For foundation, you can do it with M20, but here M35 is being used because Chennai is a coastal region, and also in the soil there are chloride contents, and chloride contents are deleterious to the concrete and the reinforcement, and therefore higher grade of concrete. Higher the grade of concrete, you make the concrete more impermeable. Then structural frame, the design basis for structural frame is, it's a dense concrete, and basically the advantage of this technology is that the columns are hollow, and those columns are erected with beam, and then there is bed jointing. Let me tell you here that whenever we do precast construction, there are two kinds of joints. One is bed joint and one is dry joint. Dry joint means that you connect beam, column, slab, and other things using nut bolt, or using nut bolt, I would say. Or there's another thing is where you have this kind of system, which I will show you in subsequent slide, where you have these shells, you have dowel bars protruding from slab, column, and from beams, and then you lay a screen and do the wet jointing. So this wet jointing is preferred in a country like India, because we have rains, and our country is also seismically prone. So this kind of wet jointing will ensure monolithic joints. So monolithicity of joints is the most important thing when we are talking about precast concrete construction. So wet jointing will ensure monolithicity. Another thing, when you are doing concreting of jointing, it is very difficult because these joints are very small and concrete, compaction of concrete, putting that concrete into those joints, ensuring proper curing and the setting of concrete. All these things are something which need to be attended to. So what is being done whenever we do the wet jointing, we normally use grouts, or otherwise we use self-compacting concrete. I have a slide on self-compacting concrete as well, which I will also explain. So the self-compacting concrete is a flowable concrete which can directly be put into the joints, and it will set and gain early strength, and that will ensure monolithic rigid joints. So when we design the building, we design the buildings for the loads. So depending upon the uses of building, because it's a residential building, so you will have a live load for this, for which we have a Indian standard, number one. Secondly, there are other loads like seismic load, earthquake load, wind load, and if you are doing something in the hilly regions, so you may have snow loads also. If you're doing something in coastal region, then you can have you will have the coast cyclonic winds, so that also need to be incorporated here. So being in Chennai, and what you see in right hand side is the wind hazard map of India, which is primarily based on National Building Code 2016, and this is from Building Materials and Technology Promotion Council's Vulnerability Atlas. So you see this map, and from this map you pick up the wind velocity, which is 50 meters per second for Chennai case, and then based on that basic wind speed, you find out design wind speed. And again, this formula is given in IS 875 Part 3, which is the Indian standard. And as I was telling you, if you are constructing a building in cyclonic region, so there is a factor which gives due consideration if you are constructing or building a structure in cyclonic region. So there are four factors: risk coefficient, size factor, depending on height and size of the building, what kind of topography, and importance of the building. So you find out design wind speed, and then design wind speed can be converted into wind pressure, and that wind pressure, when multiplied by the exposed area, will give you the wind load for which your building needs to be designed. Now, the next important load is earthquake load, and what you see in the right-hand side is the earthquake hazard map of India, and India is divided into 4 zones. Chennai falls in zone 3 as per seismic zone, and this map which is shown here is taken from Vulnerability Atlas of India, which is published by Building Materials and Technology Promotion Council. India being a seismic prone country, and looking at the history of earthquakes in India and incurring losses to lives and property, it's very important that whatever building we design, it has to comply with the existing national standards, and the design should be based on those standards. So here, most important thing is that you need to design your building ensuring ductile behavior. And ductility ensures that in the event of an earthquake, the inhabitants of the building get sufficient time to come out of the building. And ductility means that sudden collapse of building is prevented. So that is first and foremost thing, and there is a standard ductile detailing code is there. If you are doing a building in reinforced concrete, then you need to put in use 13920. Then there is most important code, Indian standard, which is 1893/2016, which gives you different factors for designing your ductile structure, your moment resisting frames and ordinary moment resisting frames, RCC shear walls, and things like that. So here in Chennai, the design basis is that the entire precast concrete construction or the entire building is designed as a dual system with RCC structural walls, ductile RCC structural walls, and spatial moment resisting frames. And the moment you invoke spatial moment resisting frames, the response reduction factor, which is very important, is taken as 5. Apart from this, there are other factors. One is a tuning factor, because it falls in seismic zone 3. So the tuning factor is 0.16. Building I is the importance factor. Here it is taking slightly on a higher side, 1.2. And then damping ratio is 5%. So based on these parameters, we can find out design horizontal seismic coefficient. Again, This the equation is given in IS 1893, which says Z by 2, SA by G, I by R. So I is that importance factor, R is response reduction factor, Z is the zoning factor, and SA by G is again um, uh, is a design acceleration coefficient, which is depending upon the soil condition and depending upon the time period of a building. You find out SAG from a response spectra curve, which is again given in 1893, and you ascertain design horizontal seismic coefficient. And this design horizontal coefficient, when multiplied by the seismic weight of the building, which is a vertical load of the building, it will give you the horizontal shear for which your building needs to be designed. So I would again like to repeat this, that we have to design our building for a horizontal load, which is, a fraction of your vertical load. And that fraction is found out from this equation, which is dependent upon the zone in which your building is lying, depending upon the structural configuration, importance factor, and the kind of ductility and the kind of moment frame you are using. Depending upon all those things, you can find out the base shear. And then that base shear is distributed along the height of the building, and then you carry out the structural analysis and design, which I will cover in the next slide. There are dedicated softwares nowadays available through which you can carry out the analysis. And what is analysis? Structural analysis is something where when you apply the load, you will get the bending moment, shear force, axial force, and other torsional forces and other forces for which each structural element can be designed as per IS 456. So here the building is designed as a moment resting frame, and this is the base shear for which the building is to be designed. Also, as I explained you earlier, that the slabs are precast, partially precast slabs are being used with the reinforcement, and that reinforcement is connected on site through a screed to make it a composite structure. So, composite frame is also one of the design basis criteria. For any analysis and design, what is the grade of concrete is also very important. So here, M35 and M40, normally these are higher grade of concretes. And as I told you in the beginning, that whenever we are using precast concrete construction, we use higher grade of concretes. And here we are using M35 and M40 grade. Just to explain you, M35 means 35 is the cube strength, and 35 means 35 Newton per mm square is the strength of a cube of this concrete grade. So floor elements are M35, and vertical load bearing elements are M40 grade. Based on this design basis, as I told you, that a model is created in the computer through CAD softwares, and there are umpteen number of softwares available nowadays. Some of them are written here: StatPro, ETAP, SAFE, SAP, Abacus, and for this project, ETAPS is the software which is being used. And once you know the loads, you know the dead load, live load, you know the earthquake load and build load, then your building is analyzed and designed for so many load combinations. And if you, wind load and earthquake load, one load acts at a time. So you have to design, you have a load combination, dead load plus live load, then plus minus, earthquake load, or plus minus wind load. So for these load combinations, so if we consider only earthquake load, there are 13 possible load combinations for which building is analyzed, and then for the worst possible scenario, your design is carried out. Also, depending upon the configuration of your building, whether it is regular building, whether it is irregular building, you need to carry out the static and dynamic analysis. Again, these softwares are so good, and they help you in carrying out static and dynamic analysis. And another analysis criteria is linear and non-linear. Again, IS 1893 gives you criteria when to carry out linear or when to carry out non-linear analysis. So based on these softwares and based on these load combination, and again, you can model your building 3D. So this is a 3D model. Otherwise, you can do a 2D planar structural analysis. And idea here is to get the design forces for each and every structural element, for each and every joint, and then design based on Indian standards those joints and those columns and beams. Okay, and again, these softwares nowadays incorporate Indian standards, and through these softwares, automatically for worst possible scenario, you can design your building. Also, the AutoCAD is another software which is very important nowadays. Earlier, drafting or the drawings were made by draftsmen manually, but nowadays through AutoCAD, you can generate all the drawings. In fact, some of these softwares are automatically connected with AutoCAD. So once you do the design, you will get the structural design made uh, based on the design. Let me also briefly tell you about the concrete mix design. There are two kinds of, mix design. One is nominal mix design, and another one is design mix. So one is nominal mix and design mix. Earlier, if you are using a lower grade of concrete, suppose M10 or M15, then you can have a nominal mix design. Nominal mix design is given in IS 456, which stipulates, suppose you are doing M15 grade concrete, then you have to, mix concrete aggregate, fine aggregate, and the coarse aggregate in the ratio of 1:2:4. So that is a nominal mix. It's a prescriptive guideline which is given in Indian standard with minimum, water cement ratio and minimum cement content. You just mix one in a ratio of 1:2:4, your cement, fine aggregate, and your coarse aggregate, and you get the mix. So that is called nominal mix. But over the years, it has been found that there is a wastage of material, and you don't get the desired performance parameters of concrete if you do it with nominal mix. So nowadays, most of the buildings, when you are doing such a large project or where there is such mass use of concrete, you normally go for concrete mix design. And concrete mix design, again, there are Indian standards available. Based on those standards, you can do the mix design. And as you can see, this is the mix design for the M40 and M35 concrete for the Chennai project. And I have been repeatedly telling you that concrete mix design and quality of concrete is of paramount importance, because primarily your all structural elements are made of concrete, and so if the quality of concrete is not good, your structure will not comply with the performance parameters. Okay, and another salient feature, a special feature of this project is that we are using GGBS. GGBS is ground granulated blast furnace slag. And this slag is a byproduct of our steel industry. So it's a waste material which is being added in the cement up to 15%. The cement is replaced by GGBS, and this GGBS being finer pozzolanic material, it gives better strength, and we save cement. Also, the concrete which is made using this waste product is green and sustainable. Also, admixture is used for quick setting and for early strength. In precast component, what happens when you cast these elements in the factory? You require early strength. Normally, early strength will enable you to demold your structural elements early, and then you can do the curing, and then you can take them those components to the site. So for early setting and for early strength, admixtures are being added. Also, you see in this slide, we have written M-sand. M-sand stands for manufactured sand. In the region of Chennai, you don't get river sand, so you have to use manufactured sand. Manufactured sand is nothing but, it is a quarry, and it is made of quarry and stone dust. So manufactured sand instead of natural river sand is being used here. And, as I was telling you, M40 stands for, compressive strength of cube of concrete cube, 40 Newton per millimeter square. And by using this, concrete mix design, we are, achieving the concrete strength at 7 days 46, which is far above than your 40. So the entire material optimization, use of waste material, use of admixture for early strength, and getting better compressive strength, make your concrete and the design sustainable and green. Normally, when you do a big project, a batching plant is also installed at the site. Briefly, if I have to explain you the batching plant, through batching plant, you are industrializing the production of concrete. Otherwise, what happens if you go to the old times where we used to have artisans at the site? So what we have, we normally just by weight or just by guess, we mix concrete. We make concrete by mixing cement. One bag of cement with so many. There are wooden boxes through which material, aggregate, and sand are measured, and then over a platform you mix all those things and then add water. And there are thumb rules through which concrete is being made. But that is not a professional way of making concrete. The professional way of making concrete is through batching plant. And what you see here, these are the silos which keep aggregates, fine aggregates, coarse aggregated cement, and then through a weighing process, automated, very accurate weighing process, you mix all these components and then make the concrete. So that is about batching plant. Now, based on this design basis and based on the technology which I told you, let's move to the next step. And next step is casting of precast element. It is also very important that casting is of these elements are done in strict controlled conditions in the factory or casting yard. Also, if you happen to visit any casting yard, you will find modern sophisticated processes being employed for casting of these elements. Let me take you through the factory setup. This is a slide from BG Shirke's plant at Chennai itself, and this slide shows you these are the beam and column elements, and this is the reinforcement. So this is a mold, this is a steel mold, and then you lay the reinforcement cage, and all these cage are automatically made through modern machines, and very accurate one, and then you do the concreting. And once concreting is done, then these beams are, these molds are demolded, and then these beams and columns are cured through autoclaving. And curing is also fast here. It is not a natural curing with water, which we do normally in case of cast in situ construction for 7-14 days. Here, the curing is expedited by through a chamber, in a chamber, under pressure and under heat. So what you do, curing is curing is done through autoclaving. And autoclaving is nothing but pressurized heated curing of these structural elements, which enable fast gain of strength and early demolding, and then early use of these structural elements. Okay, so all these elements. And another thing I want to emphasize here, this setup is like automobile setup nowadays. Everything can be done in an industrialized fashion. So you have workforce employed, and then each the person is given a special task. One person will put a steel cage, one person will check the steel cage, then there will be automatic hopper through which concrete will be poured, and once concrete is poured, the next day it will be demolded, and then it will put to a curing chamber, and once it is cured, then automatically it will be hoisted and it will be stacked. Okay, so what you see here is the reinforcement cage, and the moment you reach here, you see the concrete is being laid. And what you see on the upper side, these are the intentionally left U bars, so that you can connect it this with the slab to ensure monolithic action. This is casting of slab, again partially precast slab. So this is a huge setup. Again, the picture is from BG Shirke casting yard at Chennai, and you can see all these things are automatically being done. So these are casting tables where reinforcement is being laid, and this is a concrete hopper through which concrete is poured, and all openings and everything is pre-decided. You can in fact put the service lines also, service lines also here, and then do the concreting. And once the concreting is done, then they are automatically moved further. And what you see here, this is a curing chamber. They are put in the curing chamber, and once curing is done, they are stacked outside and then transported to the site. And all these, in fact, for cutting, for dimensional accuracy and all. Even robots are being used, and laser cutting and laser marking of these slabs to obtain highest dimensional accuracy and highest dimensional, reinforcement laying and other things. Also, let me tell you another thing, because these elements are thin and these are RCC, reinforced concrete. So there are two components. One is reinforcement and another one is concrete. So we need to provide sufficient cover to a reinforcement whenever we are doing any structural element. So when you do a cast in situ construction, sometimes it is found that the cover is not properly maintained. But in this kind of controlled condition and factory setup and in splice system, there is a proper cover which ensures better durability of RCC construction. Now, once you do the construction, this is how this is a table which is being tilted. So this is a precast slab, and again the stacking of these elements, precast elements, is very important, because there should not be any damage to these elements during stacking and while transporting these elements to the site. So everything has to be decided beforehand, and how stacking is to be done. Stacking is to be done in such a manner that you can do the curing. There should be proper air circulation. So this is how curing is done, and this is how you can see here. This is how through a crane gantry girder you can just lift the partially precast slab and stack it further. This is the precast staircase which is being lifted, and these are the precast columns. So this is how casting is being done. Now, once you do the casting, then the casting, and when the elements reach to their strength, then you transport these elements in a specially made trailers. Okay, suppose you have a big element, then you have to use A-frame. Otherwise, if you are long trailers, you have to use, and these elements need to be transported to the site, and then at site these elements are erected, aligned, and then wet connected to create an entire structure. Okay, so in this project in Chennai, I will show you through actual on-site photographs the various components, what is the present status and how they are being connected and other structural details. So these construction sequence again is divided into mainly two parts. One is substructure, another one is superstructure, and substructure is your foundation part. Okay, so the foundation and the structural system up to the ground level, so that is called substructure. And above the ground or above the plinth you have superstructure, which again comprises of structural system, floors, and your wall panels, and then a slide on plumbing and electrical and the finishing. So let me just show you those photographs. But before getting into those site photographs, most important thing once you do the design and execute it in the field is structural drawings. Detailed structural drawings need to be made available to the site engineer, and site engineer should be sufficiently educated to read these structural drawings. It is very important that how these structural drawings are being read or are being referred. So this is a structural drawing which gives you foundation layout. So because you have a ground which is you have to prepare that ground, and you have to locate all the foundations accurately. So what you see here, this rectangle, if you see, so this is the center point of your foundation, and this is the pit. What you see dotted is a dimension of a pit, the pit which you excavate, and this the line which you see here, the solid line, this is the outer boundary of your foundation plan. Okay, so this is typical foundation plan, and so you have to refer this foundation plan. Then you have to carefully mark these center points, and then you have to carefully excavate, and then carefully mark, put the molds, and then do the concreting. And here, as I told you earlier as well, that the foundations are cast in situ. In times to come, you can also cast these foundations in the factory and then put it over the site. But right now we are not doing it because of differing soil conditions across India. And these are typical structural reinforcement details of the foundation, because here we are using isolated foundations. So these are the reinforcement, how the horizontal reinforcement is to be laid, and how this reinforcement is to be connected with the column which will be erected over this foundation. All these details are given here. And let me again tell you, there are 2-3 codes which are very important. One is IS 456, another one is 13920. So these codes in detail give you how the connections are to be made, what is the length, lap length, what is the length which will go into the beam, what is the length of connection between the foundation slab and the column. So all these things are given in these drawings, and then these drawings are being referred, and according to these drawings, reinforcement cages are laid, and then concreting is being done. There is another thing. If you see this is called stirrup, and in case of earthquake, stirrup also plays very important role. So proper tying of stirrup and proper spacing of stirrup is also of paramount importance when we talk about earthquake resistance. So all these details are given in these drawings, and these drawings are prepared with AutoCAD. So these drawings are given to the site engineers, and depending upon these drawings, structural drawings, detailed drawings, and these are called section, and this is a foundation layout and plan. So based on these sections and plan, you can start doing the foundation work. Also, let me tell you here, because this is the implementation of new technologies, all these drawings need to comply with Indian standard, number one. Then secondly, these all drawings need to be vetted by a third party. And in our case, the third party is IITs. So all these drawings need to be vetted by IIT. And as you can see, this blue stamp here, it's a sign of a professor from academic institution, preferably a structural engineer, which certifies that this drawing is prepared based on prevailing Indian standard and comply to the specification given in the contract document. So that is also very important, vetting of structural drawings. Just to show you in detail, again, the picture, this is the section, and this is how the concrete, this is how the foundation, and this is the column, and this is the plinth. So let me again, devote few minutes here. So this is your foundation slab. So this is an isolated footing, and this is the reinforcement cage which is put in the horizontal direction. And this reinforcement which is put, the horizontal cage, it has to, bend like this. Okay, this is also very important, which is given in code. Then once you lay the horizontal reinforcement, then you have to put some vertical bars, which those bars will be connected with the stem column. So this is, first you laid the PCC. What you see here is M10, plain cement concrete, just for leveling the ground, because ground is normally undulated. So for leveling the ground, you lay the PCC. Over PCC, you make this isolated footing of foundation slab with dowel, with bars, vertical bars inserted, and over these vertical bars, this column. So this can be called a stem column, or this can be called as a normal column. This column is laid up to the ground level or to the plinth level, and at the plinth level, again, a plinth beam is put. Again, this is precast, this is precast, and this is cast in situ. So you put the vertical bars, and then you lay the stem column, and then you put the plinth beam, and then you do the wet jointing here and here. What you see here, this is the cast in situ. This is precast, and then this concreting is done on site to ensure monolithic behavior. And as you can see, this bar is going inside the column, so that this beam and column behave together. Okay, so that is called monolithic action, and these things are written here. As you can see, if you have isolated footing and if the columns are nearby, then isolated footing is converted into combined footing. That means that for both the columns you will have same footing, so that is called combined footing. And here the safe bearing capacity used is 25 ton per meter square, and as I told you, that PCC is laid, and over which the depth of foundation, again as per structural design, here in this case it is around 450 millimeters millimeter or 45 centimeter is the depth of the footing. Okay, and the grade of the concrete is M35. Also, Chennai being coastal region, so all this reinforcement which is being put here is put with anti-corrosive coating. And the soil, once you analyze the soil, it was found that it has high chloride content, and high chloride content means that it is corrosive in nature. So you have to do anti-corrosive nature so that there is, onset of corrosion is prohibited. So that is another important thing which need to be done if you are doing where the water table is high or in a corrosive environment or where the chloride content is high. Also, all the exposed surfaces, because this will be directly, and once you make this column, this entire portion will be backfilled. Okay, backfilling means whatever soil you have excavated, that need to be filled again with, in layers with proper compaction. And this soil being high in chloride content, in all these exposed surfaces have been applied with bitumen paint before refilling. Okay, so all these concrete exposed surfaces are coated with the bitumen. All this reinforcement, before laying this reinforcement, they are coated with anti-corrosive coating. Okay, and with this, let me show you the picture of actual site picture. So this is how excavation is taking place. Once you do the excavation, refer to the structural drawing, do the layout, and then do the concreting for foundation slab, and then bring the stem columns and plain beam and erect those. So one by one, I will show you all those pictures from the site. So again, this I wanted to show you here because when it's a coastal region, number one, Chennai. Secondly, the water table is high in coastal regions, so normally during rainy seasons, water table becomes high, and when you are going deeper, the water comes out from the ground. So how to do the concreting here? You have to run the continuously. You have to drain this water through water pumps, and sometimes to stop the use of water, you have to use bentonite slurry so that the water which is pouring out, oozing out, can be stopped. So continuous while laying the foundation, you have to pump out or drain the water, groundwater. So this is how the excavation pit look like. And once you, another thing, once you excavate the pit, you have to stabilize these walls. Okay, these soils. Okay, if it is a clay soil, then it can be stabilized as it is. Otherwise, you have to compact it so that while doing the foundation, it should not cave in. Okay, and so this is how the PCC is being laid, and as I told you, PCC is just for leveling the ground. Okay, so 100 mm thick PCC, which is normally M10 or M7.5 concrete, which is laid, and just to make the surface plain. And this is that dotted line which I wanted to show you. Over this, you will lay the foundation slab. Okay, and another special feature of this project is because the bearing capacity is quite high, 25 ton per meter square. So normally at the site, once you start excavation, so where you are going to lay your foundation, you do a plate load test just to ascertain the bearing capacity which you have used for your structural design. Okay, and safe bearing capacity, another catch is if you find through plate load test safe bearing capacity less or more. If it is less, then you design for the bearing capacity which you have. If it is more, then you can design it for more. Okay, and so here just to show you, it's again a good practice that to be doubly sure about the bearing capacity, you do the actual load plate load test, which gives you the actual safe bearing capacity of the region. Now, once PCC is laid, this slide shows this is a reinforcement cage, which I was telling you. So this is a horizontal vertical reinforcement, which as per your design for the worst load combination, So in a reinforcement cage, what is important? The dia of the reinforcement and the spacing in both the directions. That is important. And secondly, this length. Again, this length, how much length is to be left, that is again given in quotes. So that is also very important. So once you lay this reinforcement cage, then you put this vertical reinforcement, which will go into the stem column. And again, why these bars are being left? So that this foundation and this column acts together monolithically. So structural integrity is very important. To ensure that structural integrity, we need to we need to have this kind of retaining. And this vertical bar is also, put like this. So again, this entire thing is given in code that depending upon the diameter, what should be this, lap length. Okay, so this is called lap length. So this length is again decided, and then this kind of thing is then done. And after this, the concreting is done, cast in situ. And these are, you can see these are isolated footing, and then if you combine two footings together, if you cast, then this is called combined footing. So after laying the reinforcement cage, you do the concreting, and once once the concreting is done, so this is how your foundation slab looks like. And you can see this is the reinforcement which is left in the footing, and over this reinforcement, this stem column is being laid. Okay, and so this vertical reinforcement and then the reinforcement of this column are connected together, and then wet jointing is done so that there is a monolithicity at this joint. It is a closure loop. This you can see, this is the isolated footing or a foundation slab, and then this is that stem column. Again, as I told you, that stem columns are made in the factory or in the casting yard, and then they are transported and aligned and erected at the site like this. And again, there is a notch here over which the pin beam will come, and here the reinforcement of this stem column will be connected with the reinforcement of your foundation slab. So, and then the concreting will be done at the site. So this slide shows you, and this is that bitumen which I was telling you, because it needs to be backfilled again. So bitumen is being put here because the soil has a higher chloride content. Also, all these column cores, their dimensional accuracy is very important. So there is a welded wire mesh which is being used, which I will show you later, to maintain that the inner dimension of the column need to be maintained accurately. So for that, there is a welded wire mesh, which is equal to the size of your column core, stem column core, which is known as extra mesh, which is put inside. Okay, and then this is how it looks like. Once you make the foundation, then you do the stem column. Okay, and you can call them, there are various nomenclatures. So sometimes a small pedestal is also made, but here, you are just connecting your foundation slab with this stem column, and here you are making it, connecting it with the plinth beam. I will show you in another slide. Also, the typical size of a stem column is 450 by 450 mm, and the height is up to plinth level. And the bars in this are 4 bars of 20 dia and 4. So there are 8 bars of 20 and 16 diameters, which are put as vertical reinforcement, which are connected with stirrups here. Clear reinforcement, because it's a corrosive environment. So reinforcement, again, there is a table given in IS 456, which says that in a hostile or an aggressive environment, the minimum clear cover to the reinforcement should be 40. And this cover is also very important, because if you give insufficient cover, your building will get corroded, and your life of the building will get considerably reduced. Okay, and again, as per Indian standard, the ordinary Portland cement is being used, which is normally 43 grade cement is used, but for foundation below ground level, OPC cement of grade 53 with C3A content 5 to 8%, calcium alumina content 5 to 8% is recommended here for stem columns. right, for concreting below foundation. Now, again, this is a picture from the site. Already this project has started in January, and already we have reached up to the fifth floor in this project. So once you do this stem column, then what you do, you do the backfilling. And as I was telling you, this black thing is a bitumen layer, and after doing that bitumen layer, you do the backfilling. So now this is a plinth level where you will put the plinth beam. Okay, and you normally put a Haitian cloth to do the to protect your reinforcement, because if you are in a coastal region, the reinforcement, although you are putting an anti-corrosive coating, but because of ingress of water and other things, this may get corroded. So Haitian cloth is being put for curing as well as for protecting this reinforcement from the corrosion. Now, after this backfilling, I showed you those notches, and in those notches, this plinth beams are being put. And now it is clear to you, this is a plinth beam, and you have reached up to a plinth level, and then this is that column, and these are those hollow, hollow core which is left, and now here the concreting will be done. So the advantage, this is the uniqueness of this technology. Here, you will do the wet jointing, means these joints will be filled with self-compacting concrete. And the moment you are putting a reinforcement here, and you are doing wet jointing through self-compacting concrete, it means you have made this joint more or less. The other practice which is being used is nut and bolt connection. So what you do in these beams and columns, you put a plate, steel plate, and through nut and bolts and then you grout some bars, and then those bars are connected through nut and bolts. So that is another type of connection. But I recommend that whenever you are doing the precast concrete construction, always go for wet jointing, because wet jointing means a little bit of cast in situ connection, which will ensure structural integrity at the columns, at the joints. Okay, so after erection of these hollow core stem columns and these precast plinth beam, they are put in these notches and then do the concreting. Just to give you another view of this, is also very important. These columns and these beams, their reinforcement need to comply with the standard, that is IS 13920, which gives in detail the detailing of your column reinforcement. And detailing is very important to ensure ductile behavior of any RCC element, whether it is beam or whether it is column. Okay, so this is the kind of detailing which is to be done when you are connecting two bars. Then how it is to be detailed, what should be the spacing of your stirrups, all these things are given, how stirrups are to be bent, how many bars are to be put. All these details are given in this drawing and can be read from these drawings. And for foundation, we are using M35, and whereas for columns and beams, we are using M40. And I already told you that the clear cover is 40 mm. Okay, and stem columns are 450 by 450, whereas the size of column above ground is 350 by 350 mm. Okay, and these hollow core precast columns are filled with self-compacting concrete, and that concreting is done with beam and columns, with beam and slabs. This is that hexa mesh I was talking about, when the casting of column is done to ensure that dimensions, internal dimensions accurately. This welded wire mesh is inserted. So you can see this if you see the section. So this is that expa mesh. Again, this is a innovative thing which is being done in this project by the agency. They put this expa, they call it expa mesh, which is a welded wire mesh to ensure the dimensional accuracy. This is a kind of sacrificial form work which is used to maintain the dimensional accuracy. Also, a sleeve of 60 dia is created in the column at the time of casting to insert a steel rod with hook to lift the column. Now, this column is to be lifted at the side because you are making this column in the factory, and then this column is to be taken to the side and then, aligned and properly aligned and erected at the side in sync with the foundation the foundation slab. So what is done, a sleeve is created, and in this a sleeve at the time of casting is created, a 60 dia, and in this you put a steel rod and then to hook you lift this. So all these things are to be intricately designed and decided beforehand. So this is the lifting arrangement for your precast column, and similar arrangements are done for beams and for slabs, where you leave hooks, reinforcement hooks in the at few places, and through those hooks you lift the column, beam as well as slabs. Now, you can see here, once you have reached at the plinth level, this is your plinth, and then you above plinth you have to put the columns, okay, the ground floor columns, and then again you have to put the slab, and then over that another story will come. So now we have reached, this is your ground level or a plinth level. Over this now the columns, precast columns, are being erected, and you can see this is a closure look. So once you have reached the plinth level, you have erected this column, precast column of the ground floor, and then these are again beams, floor beams, which are again precast, and then they are put like this. Over this a slab will come, and again that slab will be precast, and then all these slab, beam and column will be cast together, cast in situ, but through a screed concrete, so that there is monolicity. And you can see here, wherever we have a sunshade, or this is called lintel, this is again precast and inserted in between here like this. So all sunshades are put, and this is a ground floor column with a ground floor first floor beam. They are put into notches through a proper lifting and crane arrangement. And now over this, we will put the slab. Again, a slide to show you that how connections are being grouted, or how the concreting is being done. So through a hopper, concreting is being done in already laid reinforcement. So this is a slab which is laid, and this is a column, and this is a beam, and this is how concreting is being done. Okay, so this is a bed jointing, and this is a finished stem column with plinth beam. And this is if you are putting a if beam is put like this with the columns, and here also grouting is done with notching grouts, and this is again special grouts are available of concrete. So these grouting is done to ensure this is connected with this. Okay, and this is that notch how it is being filled up. So all these connections and jointing of various structural components are accomplished through in situ self-compacting concrete, and I will tell you what self-compacting concrete in the end of my lecture. And wherever you have the smaller the course, there you can do the micro concreting, or you can do the notching grout, as per structural, and this has to comply with the various provisions which are laid down in our course. Okay. This is a typical beam column joint showing monolithic action and continuity. So this is how you can see. This is beam, and this is column, and this is that filled up. So this is before jointing. As you can see, before jointing, this is that column, and this is your exposed beam, and this entire thing is being filled with self-compacting concrete. And once it is finished, it looks like this. Various details, typical beam and column details I wanted to show you. This is that sunshade detail I was telling you. So with beam only, that sunshade is being cast, and the reinforcement, again, it has to strictly follow the ductile detailing code. So the continuity of reinforcement is very important when we are talking about joints. Okay, so reinforcement, all the reinforcement need to go into the joint, and there should be a sufficient lap. So this shows that lap, and again, it is given in the code. Similarly, this is that hook I was talking about. You cast up to this the beam and beams, and then this is left as it is, which is being cast with the slab. So these are typical beam details, and similarly, this is a typical joint between beam and column. So this is your beam and this is your column, and how beam and columns are connected is shown here. Again, the gray portion which you see is your precast one, and this is what is done at cast in situ. So this bar is left like this bar is left like this, and then with the column they are connected like this. Okay. This is staircase detail. In fact, during Gujarat earthquake, it was found that staircases also led to the failure of the entire building. So the connection of staircase with the structure is very important. So there are two kind of things: either you integrate your staircase with the existing structure, or otherwise isolate the staircase and lift well from the overall structure. So after that Bhuj earthquake, staircase, there were special clauses for design and detailing of staircases. So this is how a staircase is being detailed, and this is the detail of staircase, how reinforcement is being put, and how this reinforcement will go into the landing, that is also shown, and how this reinforcement is to be connected with precast beam, that is also connected. The basic philosophy which you must always remember, that no reinforcement should terminate at the joint. It has to go inside another structure, another structural element, whether it is beam or column, sufficient. Okay, so like in this case, this lap has to be 300 mm, which will ensure, continuity of this. So that is the thing. Because what happens normally, it is asked that joints do not behave properly in the precast element. So to answer that, the engineering solution is to provide the reinforcement well into the joints, and then doing the connection, doing wet connections to achieve monolithicity, so that it behaves like a monolithic concrete construction. This slide shows you the slab. Once you have reached at the floor level, so you have erected the column, and then you have erected this beam with sunshades and everything, and then you bring the slab, which is again partially precast, again cast in the slab. So now you are laying this slab. Once you lay this slab, what you see is this reinforcement. So nominal reinforcement will be put here, and the entire thing will be cast with screed, and the joints will be filled with self-compacted concrete. So everything is precast, but jointing is being done at the site to ensure mobility. So this is the beauty of this technology, or this is the uniqueness of this precast concrete construction, because here most of the work you are doing in the factory, but jointing you are doing at the site with cast in situ and high performance concrete. So after erection of beams and columns, precast slabs are placed, and another important thing is bearing. Bearing means what should be the land support. How much should be the width of the support of this slab with the beam? So that is called bearing. So again, bearing, for bearing you need to refer to the code, and minimum bearing when you are putting slab over beam is given in code, so that bearing need to be ensured. If you don't provide that much bearing, what will happen? Your slab may fail in shear. Okay, because of that, there will be a bearing failure. Okay, and this is a typical reinforcement detail. As I have been, I'm time and again showing you these structural drawings, because the structural drawings are the most important drawing, which need to be referred time and again if you want to assure quality at the site. So that the structural drawing is given to site engineer, and whenever quality check is being made. So this structural drawing is being referred and seen to see the spacing, see the diameter of reinforcement, seeing the lap lengths and other details about the reinforcement. So this is a typical reinforcement detail of a column, and as you can see, these are those lattice, the rubber lattice bars which are being left, and then here the reinforcement is put in horizontal and vertical horizontal directions, and then screed is put over there to ensure monolithic or structural integrity. And if you see in section, it looks like this. So this portion is cast in the factory, and this portion is left where the horizontal reinforcement is put at the side, and then screeding is done along with beam and column. Okay. Again, as I was telling you, the cover through the reinforcement is very important. And whenever you are doing a slab, the reinforcement as per Indian standard is 20 mm. So 20 mm reinforcement is to be provided here. And wherever you have discontinuity of reinforcement, then you have nowadays splicing can be done mechanically, where two reinforcement can be connected together. Because suppose you are putting this reinforcement and this reinforcement is broken, discontinued here, and you have to put another reinforcement. Then at the point of where we are putting two reinforcement, they need to be properly joined, so they can be joined through mechanical splicing. So that is also given. And this lap length is also very important, that how much this bar should bend, that is called lap length. And normally this is 40 times the diameter of your bar which you are using. So that lap length is also very important to ensure good earthquake resistance. Then how typical the beam and slab are connected. This is the detail. Again, this gray portion is precast, and that's the portion which you see above. This is concreting, cast in situ concreting, and this is your beam, and this is your slab. So what is being done? This reinforcement is this is that hook which is coming, and through this hook we put a bar, and then we do the concreting. So now, because of this bar and because of this hook and the reinforcement, horizontal reinforcement, this joint becomes monolithic. Means this is fully integrated with slab and beam, and it will behave monolithically. Okay, and this is that lap length I am talking about. So this is a minimum lap length which need to be provided. Means this bar from here, it should at least go 0.3 times the length of this span, 0.3 times of this span. Suppose this is 3 meters, so 1 meter is the lap length which need to be provided. Okay, and this is the bearing I was talking about. So minimum bearing is again given in the code, so that if you don't provide this bearing, the slab will fail in bearing pressure. So that bearing need to be provided as per code requirement. So this is a slab, this is a precast beam, and then how it is to be put, and then this kind of hook which we are putting, we put a reinforcement in horizontal direction, and then we do this inverted beam kind of thing, and this casting is being done. So this is how floor and slab are joined together. And why I'm showing you these drawings, because jointing is the most important thing in precast concrete construction, and joint will dictate the overall behavior of your building. And this is a panoramic view. Now you can see here, this is the column, this is that beam, this is that sunshade. Then we have laid that slab, and as I was telling you, the partially precast slab, and these hooks are left, and on these hooks that horizontal reinforcement will be horizontal reinforcement in both the directions will be laid, and then that screed and the jointing, all these columns, core of columns and these beams, they all will be cast together, cast in situ. And in between also, these are called lattice beams, which depending upon the span, the reinforcement is put, and this is cast with the screen. So you can see here, this is the reinforcement which is being laid. You can see here. Yeah. Okay. So this is the reinforcement being laid, and then the concreting will be done. That concrete is a high performance concrete. Normally here the screed, the thickness of the screed is 55 mm thick, which is put over this to ensure monolithic and ductile behavior of the structure. And once you do the concreting, then you have to do the curing. Curing, friends, is very important for concrete structure. So structural integrity and monolithic behavior is achieved in this technology through wet jointing. I have been repeatedly using this word because this is the uniqueness of this technology. And dowel bars are the bars which are protruding or left while doing the precast in the factory or in the casting yard, and through those dowel bars are connected with the reinforcement which is laid at the site, and with the reinforcement of other structural components. Okay, and those joints are filled with concrete of higher strength. Okay, so this is again a view, and once the screening is done, then you have to do the curing. Next is the spaces which is being created in between these frames that need to be filled. So for filling of those spaces, you need to create a wall. So in this project, we are using AAC blocks for walls. Otherwise, also you can use a dry wall, which is a sandwich panel system, which can be made in the factory. In some projects, they use precast RCC wall as well, but in this project, AAC blocks are being used. So AAC blocks have direct advantage over burnt clay brick. AAC blocks are made with it is a lightweight concrete, and they are made with the lightweight precast foam concrete. And the composition, if you see, of AAC block, it uses gypsum, sand, lime, cement, water, and aluminum powder. This aluminum powder reacts with cement and to create foam, and it becomes a lightweight concrete. And its density, if you compare the density of AAC blocks with the brick density is 1900 kg per meter cube, and here the density is 450 to 550. It is very light in weight, and being light in weight, it reduces the wall, the load of wall is considerably reduced, and therefore you have a less load on the foundation. So your foundation design is optimized. And AAC blocks, because being foam concrete, they are better as far as functional performance is concerned. Means acoustic and thermal wise, they perform better as compared to other thin elements. So AAC block is another very important feature of this project. So all these infill walls are of AAC block, and because we are using lightweight AAC blocks, so they are non-load bearing walls. Another thing, the typical size, these blocks are slightly larger as compared to brick. Brick is your 230 by 150 by 150 by 150 by 75 mm, whereas these blocks are 600 by 200 and 150 mm. So being larger block size, you can speedily lay the infill walls, and being larger, there are less joint, and there is less consumption of mortar while laying those walls. So there are several advantages. So AAC blocks are being used. Another important thing which I want to tell you, there is a word called autoclave. So autoclaving is spatial curing, which means autoclaving is nothing but curing under heat and pressure. Normally, if you do curing, curing takes 14 to 28 days, and normally it is water cured. Concrete elements are water cured. So it's a time-consuming process, and to do fast curing, what is being done, curing you can do under pressure and under heated conditions. So normally in pre-casting yard, you will find curing under heat and pressure, and that is why within no time you can manufacture these structural elements, because curing is done under heat and pressure. Quality control is the backbone of any construction which we do. So for all these projects, all the agencies need to install a quality control lab at the site, and typical quality control lab at site comprises of host of equipments. This which you the photograph which you see here is a compression testing machine, where at the site, once concrete is very important part of this entire precast concrete construction. So whenever you do any precasting, you need to ensure the quality of the concrete being used. And the quality of concrete is ensured by casting cubes, and those cubes are later tested for their compressive strength, dimensional accuracy, water absorption in the quality layer, as well as by the third party. So this is how the cube is being tested under compression in a compression testing machine. So this is a CTM, compression testing machine, and you keep on putting the load, and once it breaks, that load you capture from this machine, and that load divided by the area of this cube will give you the compressive strength. And that compressive strength of that concrete has to be, suppose you are using M40, so it has to be above M, above 40 into per mm square. So that will assure your quality. Okay. Then similarly, you are using different materials. So in this slide, you see these are the sieves. So normally sand and aggregates, their size has to be perfect, and so it is called grain size distribution. And through sieves, you can find out the kind of aggregates you are using and what are their respective sizes. In addition to quality control through this testing at site in the laboratory, then normally in the projects of such sizes, third-party quality control and assurance is also being done. And for this project, IIT Madras is assigned as a third-party inspection and monitoring agency. Now, the plumbing and electrical, because it's a concrete construction, so plumbing and electrical services are done in a conventional method, which is chasing and filling. And you can put some openings while casting the slabs and all for putting your fan and all. Fan and all. Otherwise, casting, services are done with chasing and filling. This is just a slide. There are other finishing items, and the way you do finishing of your conventional construction, same way you can do the finishing here. And these projects are lighthouse projects. So in these lighthouse projects, we are putting a lot of good practices, such as street lights, primarily LED lights, then solar street lighting. Sewage treatment plant is nowadays must, then the rainwater harvesting, solid waste management, and all other provisions which are required as per national building codes are being included in this project. This technology is also being used world over. Precast concrete construction, and everywhere in the world this technology has been successfully used. In India also this technology is being used, and the agency has shown a few photographs of their successfully completed projects in and around India. You can see this, and with this any kind of precast, another question asked is the shapes. Any kind of shape, any kind of facade can be thought and can be cast in the factory and then can be assembled at the site. So any structure, whether it is residential or whether it is industrial or whether it is a car parking or even a stadium can be constructed using precast concrete construction. So these are few projects which I wanted to show you. In Mumbai, in Maharashtra, this precast concrete construction is being used quite prominently, and for their all EWS project, they are using this precast concrete construction. So this was all about the Lighthouse project, which I wanted to share with you at the moment. But as the project progresses, we will show you through these lectures the further implementation of the technology, and we will learn together the further implementation of the technologies. Another thing being technography, you can always visit these lighthouse projects online virtually by going to this website, gstcindia.gov.in. Once you enter this website, you will get a tab of live lab, and once you go to that tab, you will get the live status. So you can go to that project at Chennai and can see the live status. For any other further information, you can always contact us on these emails. Thank you.